In this video, we're going to go over the equations of linear hydroelasticity based on potential flow. So we're going to review the equations of motion in water, and then we're going to look at how we calculate the hydroelastic response and the steps involved in calculating that response. So the equations of motion in the frequency domain are given here, where I've added the fluid term. So omega q is the incoming wave frequency. MS is, of course, the structural mass matrix, N by N. MF is the fluid added mass matrix. CF is the hydrodynamic damping matrix. KS, you can see, is I've used linear hysteretic damping here because we're doing this in the frequency domain. And so KS is the N by N stiffness matrix, and KF is the hydrostatic stiffness matrix. U are the nodal displacements, and F sub F are the wave excitation forces. So we know that the finite element method gives us the structural terms as well as KF, and the panel method is going to give us the dynamic fluid terms, the MF, the CF, and the F sub F. So the fluid potential can be written as in the following way. The term in bracket covers the spatial variation of the fluid potential, and the e to the I omega q t gives us the time harmonic variation for wave frequency omega q. Phi sub I and phi sub d are the incident and diffraction potentials, and the I omega q phi rj are the radiation potentials. Well, is the radiation potential for a unit uj e to the I omega qt. In other words, these are the waves radiated by the structure experiencing a displacement specified by u sub j with the time harmonic. So the fluid terms in the equation of motion are obtained as follows. We first want to define the so-called generalized normal. So N is a unit vector, a normal to the surface of the wetted surface. And ui is the corresponding displacement field. So it's a 3 by 1 vector, x, y, z displacements, as a result of nodal displacement I. So N transpose ui just gives us the displacement normal to the wetted surface. So only displacements of the wetted surface contribute to the fluid terms, of course. The added mass is obtained as the real part of the integral of the radiation potential times the generalized normal over the wetted surface. The hydrodynamic damping is the imaginary part of that integration. And the wave exciting forces depend on the wave angle, because the incident wave potential and the diffracted wave potential depend on the incoming wave angle. But I hasten to point out that the added mass and damping are independent of wave angle. There is no incoming wave. The added mass and damping are a result of the structural motion, not of any incoming waves. So the hydrostatic stiffness is a bit of a complicated equation, which is shown here. I'm not going to get too much into the details, but just to clarify some of the terms, NQI are the interpolation functions for nodal degree of freedom I in direction Q. Sigma Lm is the internal stress in calm water, so we always have to start out our analysis with the structure sitting in calm water, and then the hydroelastic analysis gives us the motion around that position. I'm not going to go into too many details here, but I will point out that this equation is derived in this reference here by Linda Huang and myself. Linda was a PhD student when we published this. And then the second publication here I wrote subsequently and compared different formulations for hydrostatic stiffness, because there are different formulations out there. I'd like to point out that some people only include the N3J term. If we look up there in that equation, there's an N3J in the first term there. And so some people use a formulation that only includes that term. Now, if you're going to do that approximation, it's important to calculate the hydrostatic stiffness for the rigid body modes separately, because this term just by itself does not give you the correct hydrostatic stiffness coefficients for rigid body motion. The whole equation would, but not this single term. So people that do that use the N3J term for deformational motion, but they calculate the hydrostatic stiffness for rigid body motion in the usual way that you would for a rigid body analysis. Let's discuss the situation a little bit here. So the structural matrices are very sparse. The displacement degrees of freedom are only coupled with those to which they are physically connected directly via common elements. So most of the displacement degrees of freedom are not going to be coupled with the other displacement degrees of freedom. And this is what results in the very sparse structural matrices. We absolutely have to use efficient numerical techniques to exploit the sparsity to make the problem tractable. Unfortunately, the fluid matrices are not sparse. All the wetted surface displacements are coupled through the fluid matrices. Right now, this requires a radiation problem for each degree of freedom, and that's a computationally large problem, and it's really not tractable for practical structures. In addition, I would say that the resolution is too small. In other words, if we're just talking about the displacement caused by a single structural displacement, then that displacement is going to occur over a small area, and the resolution that we would need of the fluid panel mesh would be too high. So we need a more efficient, reduced basis, and the logical one to choose are the dry normal modes, because they have a long history of being used for this purpose. Most people doing hydroelasticity do use the dry normal modes. So if we look at the reduced basis, the displacements are represented by normal modes. Only a few normal modes are required. And why is that the case? Well, the wave response is dominated by the lower frequencies. Because the wave frequencies are relatively low, especially compared to the natural frequencies of the structure, only a few modes and a few frequencies are going to be, relatively few frequencies are going to be excited by the wave frequencies. In addition, there's the spatial variation of the load. So in the single degree of freedom problem, the amplification, the dynamic response depended solely on the ratio of the excitation frequency to the natural frequency. For multi-degree of freedom problems, we saw there's two terms that dominate the response. One is that ratio of the excitation frequency to the natural frequency, but the other one, remember, is the spatial variation of the loading. So if you'll recall, PJ star, which is the excitation force in the modal equation, is equal to psi transpose P. So if psi transpose P is small, so if the spatial variation of the loading doesn't excite a particular mode, then that value is going to be small. A classic example, for example, is that in head Cs, there's not going to be any sway. That's because psi transpose P is 0. They're orthogonal. There is no excitation by head Cs for sway, at least for symmetric structure. So we can get away with using M much less than N modes. And instead of using thousands of degrees of freedom, which the structural model, which N is going to be, we can use much less than N. In fact, I've never used even 100 modes. So for the wave frequency omega q, we can write the nodal displacements uq as approximately equal to psi yq. And it's approximately equal to this because we're not using all of the mode shapes. So psi is an n by m matrix, where psi j is column j, and so we're only using m modes, so we only have m columns. Similarly, yq is the vector of modal displacements yj, and there's only m of those. So now the equation of motion was written this way, and I've used the superscript star to indicate that these are the matrices that result from applying the reduced basis. So ms star is psi transpose ms psi, and so that's going to be an m by m matrix. Ns, is, remember, is n by n. Psi is n by m, so this is an m by m matrix. And if the modes have been mass normalized, then it's the identity matrix. Ks star, again, is an m by m matrix. It's diagonal, with the diagonal elements being the square of the natural frequencies. Remember, psi j transpose ks psi j is omega j squared. CS star is a diagonal matrix with the modal damping. Now, we don't carry out this multiplication explicitly because we don't form ks, c sub s rather. So we just form the diagonal matrix with the modal damping. Kf star is equal to psi transpose kf psi, and it will not be diagonal because we're using the dry in-air mode shapes. So, but it's going to be smaller. It's going to be m by m. MF star and CF star are going to be formed directly using the radiation potential for each mode shape. So we're not going to form MF and n by n MF. And really the reason we're doing this is to avoid doing that because it's a huge amount of effort. So we're going to form MF star and CF star directly for each mode shape. And these, of course, are full matrices. Note that we can also use the same form for forces from any sort of source, right? F sub F star is for the wave excitation forces, but if the excitation comes from, say, ground motion, then we can use the same equation for seismic excitation, for analysis of seismic excitation. All right, let's discuss this a little bit. We could use the normal modes in still water. In other words, we could solve the eigenvalue problem including KF. However, I see no advantage to doing that, and I don't use that. I just use the dry normal modes, and most people use the dry normal modes. We could try to find the wet modes using MF and KF, but this is just simply too computationally intensive, and I just don't see, again, I don't see the advantage to doing that either. For a floating structure, the first rigid the first 6 modes are rigid, right? The traditional rigid surge, sway, heave, roll, pitch, yaw modes. And these, because they're rigid, the in-air frequency is 0. And usually what I do is I don't usually mass normalize these modes. And when we do that, that means the upper 6 by 6 of the mass matrix is the usual rigid body mass matrix. And similarly, the upper 6 by 6 of the hydrostatic stiffness matrix is going to be the usual rigid body hydrostatic stiffness matrix. If the structure is fixed, there's no rigid body modes, but nothing else changes. Now, I'd like to point out here that this is why I said early on in this video series that the hydrodynamics of a rigid body could be viewed as a subset of hydroelasticity. So if we're just doing rigid body hydrodynamics, we're just taking 6 modes of the structure, the first 6 rigid body modes of the structure, and not including any flexible modes or deformational modes. And otherwise, everything else is the same. Let's talk about calculating the modal coordinates for a minute. We calculate yq for wave frequency omega q and a given wave direction. For a floating structure, the first 6 values will be for surge, sway, heave, roll, pitch, and yaw. The rest tell us how the structure is deforming for different wave frequencies and wave angles. Looking at these is useful to gain understanding of the structural response, which modes are being excited by the response, by the forcing for the wave forcing, and which are not. Now let's consider a response to regular waves, in other words, determining the transfer functions or the RAOs. For each wave direction, y is a complex m by nw matrix. And the qth column is yq. Y is the matrix of transfer functions for the modal displacements. Similarly, we can calculate the transfer functions for nodal displacements very simply once we've calculated y. These transfer functions are simply going to be psi times y. So that is an n by nw complex matrix, and the qth row is the transfer function for the qth nodal displacement. Remember, psi is the matrix of mode shapes. Each column corresponds to a different mode. Column 1 corresponds to mode 1, column 2 corresponds to mode 2, column 3 corresponds to mode 3, and so forth. Similarly, we can calculate the transfer function for any response quantity. So, for example, we can calculate h tau equal to psi tau times y, where psi tau is a modal matrix for the response quantities that we want to calculate. So, for example, let's say we wanted to calculate the moment at some point. We would need to form psi tau. We would need to determine the value for that moment in each of the mode shapes, and that would form one row of psi tau. And then for different response quantities would form the different rows. Specifically, psi component I comma j, the component at row I column j of psi tau, is the response quantity I in mode psi j. Now let's talk about calculating the wet natural frequencies and modes, because so far we've been using the dry modes. So we know we would have to solve an eigenvalue problem that involves the hydrodynamic damping matrix MF and KF. However, it's just far too difficult to calculate MF. And so it's too much work to solve this problem. We can, however, easily solve the reduced problem for each wave frequency omega q. In other words, we've solved for m sub f for a range of wave frequencies omega q. We can use those values for m sub f in the eigenvalue problem. We would then calculate omega j's, but we would have to check to see how closely our omega j, our natural frequency, is relative to our wave frequency. If the error is fairly small, then that's a good estimate for the wet natural frequency. The wet modes would be then calculated in terms of the dry modes, the reduced basis. So HydroNXR does give us the capability of using this sort of approach to estimate the wet natural frequencies and modes. There's no computational advantage, however, to working with these modes. Now let's look at response in random waves. So first we need to specify the C state via some wave spectrum S omega. So typically these wave spectra have input parameters of significant wave height, significant wave period, peak period, or different parameters. Different wave spectra have different input values. So this is an example of one wave spectrum. We see from this plot that the energy in the wave field is in a certain band of wave periods in this case, or wave frequencies. I've plotted this versus period. So we see that between 5 and 30 seconds there's potential wave energy, but beyond those wave periods there's very little wave energy, and it's not going to excite response at those frequencies very much. So how do we calculate the response to random waves? Well, in the time domain, we may be interested in determining the response for visualization purposes or for some Monte Carlo type simulation. We can determine a wave elevation as a summation of multiple harmonic components. Here, AQ is the amplitude for a frequency omega q and a random phase. For any given wave spectrum, there's an infinite number of summations that we could use to define a wave field. So with the transfer functions, we can then determine the time domain response once we have the wave heights here. A more common approach is to determine the statistics of the response in a stochastic sense. So we can use the transfer functions and the wave spectra to calculate the variance for any response quantity and then obtain statistics from the variance. I'd like to point out some limitations to the current approach. We're essentially limited to linear behavior, and a nonlinear structural behavior would require a time domain analysis. We obviously are subject to the limitations of potential theory, and we also have the limitation of a homogeneous wave field. So for very long structures, may need to consider an inhomogeneous wave field, and I would like to highlight this reference here as one example of that, and this would also likely require a time domain simulation. Short duration loading is also another issue. Blast or impact loading is probably not a good type of loading to apply this methodology to. The reason is because they involve very high frequency components, and normally one is going to have to determine the response to these kinds of loadings in the time domain. So the next video is going to cover structural modeling.